Okay, good morning and welcome back. So, this may probably the last lecture in this Laplacian case. So, let me recall a bit. So, what we have introduced is the, let me go back to one more thing. So, we have introduced Green's function for the upper half plane. Now, we will and then using the Green's function for the upper half plane, we precisely got your Green's function, like your dg by d nu, and you got a formula for your solutions. So, this is the formula, which is the Poisson formula. We also introduced what is called the Poisson kernel. Okay. Using that Poisson kernel, you know that kernel has satisfied certain properties, and using that we have actually solved the problem in an upper half plane where Laplacian u equal to 0 and u satisfies the boundary condition G in the sense of limit, because u is defined only in the open upper half plane, u is not defined the boundary, but then it has a limit at the boundary, and we have shown that u is infinity and Laplacian u equal to 0 in the previous class. So, now we will show that the last part, third part of that, limit of u x equal to x naught. Let me give some ideas. So, proof of 3. So, G is bounded continuous, given that G is continuous at any point x naught, continuous at x naught, fix x naught in Rn plus or Rn minus, whatever it is, Rn, okay, Rn boundary of Rn plus. So, you have half plane. So, this is your x naught. You can view x naught as x naught 0 or x naught, whichever way you like it. Okay, that is the boundary. Now, look at the point. So, first G is continuous. So, you have x naught here. So, that x naught here. So, given epsilon positive, you can immediately see that there exists delta positive such that modulus of G y minus G x naught is less than or equal to epsilon for all mod x minus y minus x naught is less than delta. So, you have a delta here and you have I call this set to be A, this interval. This is some x naught minus delta, this is equal to x naught plus delta, and this part, the complement of it, this complement of it, this I call it B, this is B together of that. So, let me write down your formula. So, you have your u x. What is your u x? So, I want to show that I want to show x somewhere near. I want to, this is my x. So, when x tends to x naught in whatever way it is, I want to show that to prove u x tends to g x naught as x naught tends to, as x tends to, as x tends to x naught. You see, that is what you. So, we write down u x minus g x naught. U x, so we use the properties of that. So, look at here, you have the first one is k of x y, g of y, but then this is g x naught, this is on the boundary of Rn plus, okay, and then minus u g x naught, but integral of k x y is 1. So, I use that fact to write down this is equal to Rn plus k of x y g x naught, which is a constant as far as, and this integration is with respect to dsy, because integral of that everything is with respect to dsy, which we are now, which is nothing but dy prime in this case. So, if you compute this ux minus g x naught is less than or equal to, I get this thing boundary of R n plus k of x y modulus of this is positive thing of g of y minus modulus, if you want you can put it modulus if you g y minus g x naught. On A in this neighborhood it is bound thing and this is 1. So, I can write, I can split this into integral boundary is divided into A plus integral over B, and this is small, this is less than or equal to epsilon, because g y minus g x naught is less than or equal to epsilon, the other integral is equal to 1. So, you do not have to worry. So, only we have to bother far away. So, we have to worry about integral over b k of x y, okay, modulus of g of y minus g of x naught. So, let us now look at this once more. So, you have your x naught here, you have your delta here x naught minus delta, this is your x naught plus delta, okay, you have x naught plus delta. So, this is your b part. So, a y varies only here, now y is not here. So, y is here, this is your x naught. So, y will be here, x will be here, x naught will be there. So, what we will do is that in that case, okay, so you try to compute. So, you take an x close to that one. In fact, I consider an x with a ball of radius delta by 2, that you can do it, okay, delta by 2 the radius. So, my x is because anyway I am taking x limit. So, I can see within that ball. So, what we can do that, so our y minus x naught here, x here. So, you apply your triangle inequality, it is modulus of y minus x plus x minus x naught. Okay. This is less than or equal to modulus of y minus x, x minus x naught is less than or equal to delta by 2, but that can be written modulus of y minus x, this delta is y is here. So, it is here. So, y minus x will be, this will be delta will be half of y minus x naught, you see, right, this delta is then equal to y minus x naught. So, with this will give you half of modulus of y minus x naught, if you take this to the left side is less than or equal to mod y minus x. So, with this computation, so I will do a bit of computation as an exercise. So, please do this. You can show that thus I will be, you already have two terms, let me call this term. So, this term you have to calculate it, that is what you have to do that one. So, you can do that. So, you can calculate this term, this will be less than or equal to this is important, these terms are important, compute into norm of g which is bounded norm L infinity norm by n omega n, and you get a term here x n. So, to do the computation g is a bounded function. So, you can bound this. So, only we are estimating k of x minus y. This is bounded by 2 g, you can do that to the norm of g, that you can take it out. So, you are not making this small, you are trying to make this computation, you x n, you get modulus ds by mod y minus x naught. There is no singularity, be careful, be note that, okay, x naught is here, y is away. So, there is no singularity or anything here, okay. And this is also a finite quantity, finite, these are all finite quantity. So, as x tends to x naught, this immediately tells you that my x n tends to 0. You see, that is it. When x tends to 0, x tends to x naught here, x tends to x naught here, my x n tends to 0. That is very crucial. That implies this term tend to 0. That is it. That is the proof of thing. So, only thing is that you derive this estimate properly. Okay. So, that proves it. Okay. So, now let me go to Green's function for the ball. Since all the computations done in the case, you do the computations here for the Green's function. Again we use the symmetry. Okay. So, we are going to, so let me start with a ball of radius 1 centered at the origin. After that it is a dilation and a translation. So, if you do it for this one, the other thing you can write it. So, you have a ball center, this is 1. So, I am going to do it for that one. Okay. So, I use the same symmetry argument. Okay. So, this is symmetry, what is, so what we call it inversion point. So, if you have a point here x, you have an inversion point here. So, for a general ball, so let me call it BR 0, if it is a ball. So, if x is in BR 0, so you have a point x tilde, which we call it x by mod x square. This is outside and called like inversion point, right? Inversion point. Okay. Yeah, let me know why do you write. Similarly, you need R here. So, let me not write R here. We are working with R1 or B1 only. With R, you will have a parameter R here. So, let us not bother about that. You will have R square x. So, for example, if you are working with R, you will have R square here. Since we are working with 1, you will have x by, that is inversion. So, you use this is your x tilde now. So, I can still consider the recall phi, the fundamental solution phi of y minus x, and then consider phi of y minus x tilde. There is a slight difference compared to this one. So, this singularity is at x tilde, just like previous case x tilde is outside. So, no singularity in B1, singularity in B1. That implies your Laplacian of y phi equal to y minus x tilde equal to 0. But the difficulty is that when y is on the boundary, you want this to be, you want phi of y minus x tilde is equal to phi of y minus x if y is on the boundary. But this needs some normalization. This needs, you can compute this actually on the boundary. Then you see that this is not true. This needs some normalization. Okay. So, you have to add some parameter here. So, I define. So, define, this is the definition. Definition phi x of y, x is fixed, only this with respect to y is equal to phi of modulus of x is fixed, so it is a constant as far as y is concerned. So, y minus x tilde. Then this will imply it will not change the Laplacian of phi x with respect to y equal to 0 in b1 of 0 and phi x of y you get to be phi of x minus y on boundary of B1. So, you have this. Okay. So, you have here. So, still we use the thing symmetry we have used. So, with that, so you can define g x y is equal to phi of x minus y minus phi of modulus of x into so I am using this case x minus y or y minus x, as I said. Let me do it in the other way. So, both of y minus x and y minus x tilde y minus x. That is your Green's function for B1. So, you to compute so you, which is an exercise for you, compute, only thing take care of the normal properly. Okay. Compute dg by d nu y, this is what you want it at x y. I leave that as an exercise for you to compute. You get this 1 by n omega n 1 minus mod x square by n omega n, you already have it, mod x minus y power n. You compute this and then your representation formula you get it. So, that is a kernel coming into the picture. So, when so if you solve my Laplacian of u equal to 0 in B1 of 0, u equal to g on boundary of B1, B1 of 0, then the Green's representation formula ux equal to, you get it 1 minus mod x square by n omega n. So, take care of the signs properly and g of y by mod x minus y power n ds of y. This is the representation formula. Okay. So, what is your kernel here? So, if you work, so let me go to next time. So, you can do the same computation in, if you are considering BR of 0, a ball of radius 0, we get your gxy. So, you can introduce your gxy maybe. So, let me go here. So, okay. So, you can in BR of 0, if you work in BR of 0, your ux will be, so you have r square minus mod x square by r n omega n into, okay, same term g of y modulus of x minus y power n ds of y. This is the Poisson formula, Poisson formula. Okay. So, that is a Poisson, and the other one, other thing is called the, so you do not need this. So, you have the kernel in general, kernel k of x y is equal to, you have your k. So, these are all immediate things, r square minus mod x square by half n omega n and 1 minus mod x minus y power n. Okay, so you have that one. So that's the Poisson kernel. Okay, so you have your Poisson kernel. Okay. Yeah, so you have the theorem, same theorem which I am not going to prove. In this case, you don't need to assume G is bounded because G is defined on a bounded boundary. Okay, it's a boundary, compact boundary. So in a compact boundary with a continuous function gives you the thing. Assume G is continuous on the boundary, on the B1 or BR 0, and U is defined is given by the Poisson formula is given by the Poisson formula. Then 1 you have U is in C infinity of BR of 0. 2 Laplacian of U equal to 0 in BR of 0. In BR of 0, and 3 in the sense of limit. Limit again U is defined only inside the ball. So x tends to x naught, where x is inside the ball, that is how you have to look at it, but x naught on the boundary of U of x is equal to, proof is similar, you can do for all x naught is in the boundary BR of 0. So you see you have, so you understand the limit as the boundary values as a limiting values and inside U given by the Poisson formula. Okay, I think I more or less completed the topics which I plan to do it in this course, and anything further to do it we need require more time, and this particular first course does not permit me with enough time there. But then I have promised one thing in the beginning, so let me do it that one. If you recall one of my earlier lecture, we have defined the mean value property. So recall that. So if U is harmonic in the sense of whatever defined Laplace in U equal to 0, then U satisfies the mean value property. And conversely, we proved that if U satisfies the mean value property in a domain omega and U is a C2 function, then U is harmonic. So for the C2 function level, you have seen that the harmonicity in the definition and the mean value property are equivalent. So, but what we have commented at that time, to define the mean value property you do not need C2. So what happens in that case? So does the, and I commented remarked that just starting with the continuity you can define the mean value property, and then you can actually prove it. At that time there is some proof based on what is called modifiers and extra, but now using our Poisson kernel I can have a look at a different proof of that. So I can have a new general definition of harmonicity and subharmonicity using the mean value property. So let me do general definition. So I will call this is a general definition or a new definition of harmonicity. I am doing this because this is where the starting point going to be the starting point in the next PTU2 course, where we introduce the Perron's method. U belongs to C omega. You see, I am not taking C is a U thing, is said to be harmonic. In the earlier definition of harmonicity, you need, so you need twice differentiability. Of course, if you have twice differentiability, it will coincide with this definition, that is why it is called a more general, it is not different. Is said to be subharmonic. I use the inequality, mean value inequality, if Ux less than or equal to 1 by modulus of B integral of maybe any ball of Br, integral of Br U of y okay, U of y dy. Okay. This is true for all Br compactly contained in omega. So, that is where the subharmonic. Okay. 1 is said to be 2 superharmonic if minus U is subharmonic, and the reverse inequality you will get it, that is all. Okay. And 3, so I have a new definition of harmonicity via mean value property for continuous functions. If Ux equal to 1 over Br integral of Br U of y. So, I am able to define my harmonic definition using the mean value property. Okay. So, what is the advantage of this? If you look at my earlier results, if you look at my, so let me go to the next one. If you recall my earlier results of weak maximum principle, we actually used mean value property. Okay. So, I do not prove that here now. So, you can follow the similar proof. If you look at the harmonic function satisfies the maximum principles or weak maximum principles, if you look at it, the main ingredients are mean value property. So, we are for a continuous function, now we have a mean value property. Okay. So, you have the maximum principle. So, let me write it as a proposition now. I am not going to prove because it is a similar thing. Proposition, let omega be bounded open connected, be bounded open connected if U belongs to C omega bar, we take up to the boundary that we are needed, is subharmonic then the weak maximum principle is true, then the similar proof, then the weak maximum principle is true. Holds for you, that is maximum exists because U is continuous up to the boundary, is attained at the boundary, you see, d omega. And similarly superharmonic minimum principle. Okay. Harmonic, keep this in mind again and again, that is for a continuous function that I am doing, minimum principle. Okay. And if harmonic U belongs to C omega bar is harmonic, harmonic in the general sense, harmonic everything general, I am just repeating, okay, general, then you have the estimate from both sides, right. I am writing both minimum and maximum principle is true. So, harmonic means mean value property. Okay. Please understand that now the harmonic property is mean value property. Then minimum of u over the boundary is less than or equal to u of x less than or equal to maximum of u on the boundary for all x in omega. So, you have this maximum principle. Now, with that we have our final result, which I do not prove it, but you can quickly see that one. Okay. So, you have your final theorem. Okay. Omega b as above, omega b as above, and u belongs to C omega. Now, omega satisfies mean value property, that means harmonicity in it. Okay. Mean value property, so what do we do that one, mean value property or harmonic in the general sense, harmonic, both are same, harmonic, then it is harmonic in the sense, then Laplacian of u x equal to 0, this harmonic in general sense, you see, okay, with mean value property in omega, that means, and u is infinity. This is the one I skipped it. If it satisfies, you should start with a continuous function and then you define the mean value property. If it holds for mean value property, then u is infinity and you get Laplacian of u equal to 0. So, you let me sketch the proof to complete, sketch of proof. Okay. So, so you can work it out if anything is missing. You choose a point x naught in omega. Okay, so you have a domain. You have a domain. So you choose a ball, whatever be the ball inside, Pr of x naught. Okay. So you have that ball. So, what we have seen, if you are a Poisson formula to define a inside function. So, you recall that Poisson formula for a ball, recall Poisson formula. What does the saying? Using the boundaries on the boundary of the ball, you can define the harmonic function inside using just the boundary value. So, in other words, you can solve the classical harmonic function inside the ball using the continuous values of that one. So, you solve, you have to solve it, right. So, that is a major thing. So, solve Laplacian of v equal to 0 in Br of x naught and v equal to u on dBr 0 x. Okay. By Poisson formula. So, that is what we proved it now, such a unique solution exists, Poisson formula, which we already done now in the earlier class. So, V is harmonic in the classical sense. So, V is harmonic classical. Once it is harmonic in the classical sense, in fact, V is infinity, right. That is what we proved, V is infinity. We proved that Br of x naught. Okay. This V. but u is continuous. And then once it is harmonic and C infinity, it gives you mean value property. So that implies V minus u or plus or minus both you can apply. V minus u satisfies mean value property. Now apply for that big maximum principle. That is what we just now proved there. Principle implies and V equal to u on the boundary. Okay. So you can apply this V minus u, the mean value property, but V equal to u on the boundary. These are all working, you are applying the mean value properties in the Br of x naught, because you can have that thing. So we are working only on Br of x naught. So that means you have the boundary value 0, V minus u equal to V equal to u on the boundary, the minimum is 0, maximum is 0. So that implies Vx equal to ux in Br of x naught. Okay. That is the proof, because now hence u is infinity and satisfies the mean value theorem in that way, Laplacian of ux equal to 0. So I think with this we will end this course on Laplacian. You will see more on the you will see more results on the wave equations and heat equations. So this is a very little as far as Laplacian is itself is concerned. So we are not got into the potential theory yet. Okay. We have only given some basics of Laplacian, mainly we about the mean value property and the maximum principle, which gives you and the Green's function definition. So you have the whole idea is to understand the fundamental solution and the Green's representation formula, and how the Green's representation formula is used to obtain the solution in at least in 2 cases. Okay. With this for this Laplacian problem I will stop here. Thank you.